So I promise that this will be self-contained. So let me just recap some things I said last time, and then we'll continue from where we stopped, doing completely different things. So the type of object we are studying is what I call the symbolic matrix. So we are thinking of an n by n matrix, and I'll call it L for linear. And the entries of this matrix are filled with linear forms in a bunch of variables, let's say n variables. And over some field f. Today we will mostly work with C or some algebraically closed field. The question is interesting over any field. What do we want to know? So we are trying. So first of all, another representation of this kind. I mean, if every entry is a linear form with some coefficients in the field, another way to write this linear matrix is as a sum of xi ai, where the ai's are just matrices over our field, right? Just the matrices of coefficients of these linear forms. And so we will identify L with just this set of matrices, A1 up to. And the main question we are asking is whether this is, so given this set of matrices, we want to know, is L defined by its singular? So that's a singular problem. It's a different problem for every field. In fact, it's also a different problem depending on whether we are in the commutative setting or the non-commutative setting. So let me remind you, I wrote down a bunch of conditions that are equivalent for both the
Is it singular for every x?
Singular as symbolic. Symbolic.
It's the same as saying it's.
So I'm going to write down. So this is a commutative setting. So which means that the xi is the variables commute, and here we don't assume that the variables commute. And I want to write down a bunch of equivalent conditions. Equivalent. So one is just sort of the name of the problem, so L is singular. And in the commutative setting, it means over the field of rational functions in these variables. The second is that it's a field, and so we can ask about whether this matrix is factorizable. So L is k times m, where k is n by r, and m is r by n for r less than n, which we will call the commutative rank. And this factorization is again over the field of rational numbers, so the k and m, kij, mij. Okay, so these are all standard. I just want to draw the analogies to the non-commutative case. I wrote it last time, but I'll write it again. Another one is like what Zev was just saying, is that for any assignment to the variables over the field, we get a singular matrix. So for every, let's say, mu I in the field, sum of mu I ai is singular. Now as a matrix over the field, okay? And finally, that symbolically, the determinant of this matrix, of this symbolic matrix, as a polynomial, vanishes. Determinant of some xi ai as a symbolic matrix is identically 0 as a polynomial in the ring of polynomials over this field.
Maybe you said last time, what does one mean? What does singular?
Yeah, so this it doesn't mean anything. You can, it's just a name for any of these. Okay, so it's just the way I'll call the problem. We want to know whether it's singular, so I'm writing it as a condition. Yeah. So again, I'll do it here too. It's sort of meaningless. It's just equivalent to it's just a name for all the others. So here again, L is singular, but and now the field we are working on is not a field, it's a division ring, it's a what's called the skew field. And we had the notation for it. I'm not going to talk about it, but because I talked about it last time, but there is an analog to the field of rational functions. In the commutative case, only it's much weirder, and I described some of its weird aspects last time. We will not need it today. We will have our equivalent definitions to work with. So what's equivalent here for factorization? It's the same. We can factor, right? So we can factor it to a product n times r times n, where r is less than n. And this is this minimum r will be the non-commutative rank. And in the commutative case, when you ask about factorization, you naturally factorize it. It's a symbolic matrix. Its entries are polynomials in this field, and you can have rational functions in the field as factors. And you can do the same here. That would be the obvious definition, but since we didn't define this, it's very convenient that Paul Kohn proved the theorem, saying that without loss of generality, this definition is equivalent if we ask for factors in, and this is just the ring of non-commutative polynomial in the variables. So we are working here in the non-commutative setting. All it says is that monomials, the order of variables, matter. And so that's a non-commutative polynomial. And it's pretty amazing that without loss of generality in this non-commutative setting, if you have a factorization with factors who are rational numbers in this field, they are actually a factorization in which they are polynomials, and moreover, they are all of degree 1. This is a linear matrix. Its entries are degree 1 polynomials. And it turns out that without loss of generality, the factors are also of degree 1. Now, why is this important? Well, it's important for, it makes a lot of things convenient, but in particular, it makes this problem clearly decidable. Initially, and if you take this definition, if you work with a free skew field, it's not even clear that this problem, testing singularity of symbolic matrices in the non-commutative setting, is decidable. Here it's completely decidable. It's very easy to.
When you say degree 1,
I mean affine.
X, y, x minus y, y minus 1.
What?
If I take x, y, x to the minus 1, y to
There are no minuses. These are polynomials.
these are polynomials.
These are polynomials. So, 1 plus x1 plus 2x3.
Okay, so there is no inverse.
No inverses. No. These are, and so let me maybe spell out why does it mean that it is decidable. You can guess this. It means that our matrix here is a product of two narrow matrices, and each entry is an affine form, right? So you can guess or make variables of the coefficients of these affine forms, and you will just write a system of commutative quadratic equations that will tell you, whether this is possible. So it's clearly decidable. Quadratic equations, you can do Grobner basis. There's a doubly exponential time algorithm to solve this problem. And so it's decidable, and that's what we want to. I'll soon state the theorem that we have. So basically, the theorem will be that we can do it in deterministic polynomial time, but at least from this characterization, it's clear that it's decidable. And let me write a few more, and maybe I can state it already. Now, so the main theorem, we are going to get a sketch of the proof. and this is with Garg, Gurvits, Olivera, and the non-commutative singular problem, the problem written here, and this is for complex matrices. So I didn't specify how complex matrices are given, but of course if you want to have a problem in P, then you look at matrices that are rational or integer, and then you measure the size of the matrices and the size of the entries in the matrix. So P in the normal sense. And I mentioned, this is from I don't know, the middle of next year. I mentioned that there was a lot of development in the last couple of months, and there's a new theorem that is better than this. Evanius is better, is different, and Subrahmanian. That does this the same over any f is large enough. So bigger than the number of variables and bigger than n. One thing I said about, so I'm not going to show you this because that's somebody else's work. I'll show you this. One reason that this is, we find it cool and interesting is that despite the fact that the problem itself, this problem is clearly algebraic, you ask about, determinant or rank or objects that are obviously algebraic, the algorithm itself here is analytic, and I'll explain, you'll see it and you'll recognize it as analytic. It just talks about the convergence of some sequence. So it's very analytic in nature. Fortunately or unfortunately, we thought this was unique and sort of weird. The algorithm here is different and it's combinatorial. So you don't have to go to analysis to solve this problem, but you can. And this brings about some of the connections I want to talk about today of these connections to invariant theory and to quantum information theory.
They also give the approximation of the rank?
It gives, so in both cases, both of these algorithms compute the rank, the non-commutative rank. So not only singular, and you can add NC rank here, compute the NC. They also do it.
You said it approximates the rank.
No, I said that in, so this algorithm, or an extension of this algorithm, both in our case and in their case, computes exactly the non-commutative rank. The non-commutative rank, I want to talk about it a little bit later, because the non-commutative rank itself is a factor 2 approximation to the commutative rank. So it gives this approximation. Another thing I want to say about it is, right, so I mentioned the decidability of this problem because you can reduce it to a solution of a system of quadratic equations. It's a very special family of quadratic equations. It's just factoring a matrix into matrices. So it yields some family of quadratic equations. These polynomial time algorithms, what they say is that this family of systems of quadratic equations have polynomial time algorithms. This is sort of, special, rare, unique, I don't know. I mean, in general, the problem is NP-hard. So in some cases, some families of quadratic equations are solvable, and I wish I had good applications for it.
So it looks a bit weird that you multiply two linear things and you get another linear thing, not quadratic. So do you have an example, just a simple example of something that factorizes?
Maybe I can make up one, but let me tell you already that when you do it, what will happen is that some columns here will be degree 0, and they will multiply the row 0 of degree 1, and then there'll be others of degree 1. What?
That's the only case that.
That's the only case that happens. Yeah, I mean the quadratic things have to cancel anyway. It's possible to have them cancel, but that's actually what happens. Okay, so in order to get into the first the invariant theory and then into the quantum information theory, let me tell you about analogs of these characterizations. So it turns out that here, so this means that, you know, the matrix, a symbolic matrix singular, if, you know, you substitute constants for the variables and you evaluate it, you get a singular matrix. This cannot hold in the non-commutative setting because there's no non-commutativity showing up when you do that, right? So the analog indeed is replacing these constants in the field, like 1-by-1 matrices, by bigger matrices. So it turns out that the equivalent condition here to write down is that for every D, for every size of a matrix D, and for every mi matrices in MD of F, okay, so you take coefficients which are matrices and you multiply them by this, by the AIs. So now you write down the tensor product, MI tensor F AI. This is a matrix, a D by D matrix over the field. So ND by ND matrix over the field is singular in F. Okay, so what you demand here is that you take, you know, coefficients that are D by D matrices of all sizes D, and all matrices possible. This turns out to be equivalent. That's also, okay, I'll tell you where this theorem is coming from in a second. And the equivalent thing here is the same. You take symbolic, instead of variables, you take matrices of variables, matrices of commuting variables, say for every D, xi. So xi's are symbolic matrices, are D by D. D by D symbolic matrices, xi, ai, I forgot determinant. Again, as a symbolic matrix, and this is commutative. So the analogs of this is the same as what you have in the commutative case, only you have to take, instead of 1-by-1 matrices, matrices of all sizes. This is a current characterization. And the first, you know, connection we are going to get is the obvious question. It would be really, really nice to know. Questions? Gilad, you look... Yeah, because these are constant matrices. So you take AIs are constant matrices over the field, right? MIs are also constant matrices. You try them all coefficients. Like here, you try all coefficients. Also here, you try all coefficients. What this is, right? So it's a matrix over F. You want all this space of matrices to consist only of singular matrices, just like here. In the commutative setting, the matrix is singular if the linear space that they define, that these AIs define over the field, consists only of singular matrices. Here you want the same, but for all blow-ups.
So the coefficients are matrices?
Coefficients are matrices, yeah.
You probably want to
Why
say
does this make sense?
Well, it makes sense because you want to introduce non-commutativity, and the natural way is to have matrices instead of, just a second, instead of constants. But another reason it makes sense is, I may remind you, I mean, even though I'm not going to go back for it, what we did last week is that this kind of expression shows up in the definition of the skew field. So to test whether two rational equivalent expressions are equivalent, you substitute all matrices of all sizes. And then there was a Valiant-like theorem that expressions or formulas can be encoded into a matrix inverse of the same type. So it's the same, it's completely analogous.
Do you want to require also that you don't choose the
Well, it is supposed to equal 0. I'm talking about singular, I'm not talking about non-singular. Okay, so that's why I chose to define it this way. Yeah, it's more convenient. However, this is a good time to say, so suppose that L is not singular. It would be really nice to have an upper bound on the smallest d we should try in order to find a non-singular set of coefficients that will demonstrate this non-singularity. So let me denote, and this will start being important. So for both 3 and 4, which turn out to, I mean, it's clear that they are the same. It's clear just by, I don't know, Schwarz-Zippel that if this holds, if L is non-singular and this does not vanish identically, that a random set of matrices will be good. Similarly, of course, if it's non-singular and something demonstrates it, a constant set of matrices demonstrate it, and certainly a variable matrix demonstrates. So let's denote d of n, the minimal d, such that if L is non-singular and L is n by n, then there exist d by d matrices witnessing it. Witnesses for it. Okay. So it's a natural parameter to study, and okay, I will soon add some more conditions here, but at this point, I'll add just one more. But at this point, I want to note that, and the connection to invariant theory will come from the fact that this condition singular does not change if we pre and post multiply our matrices by non-singular matrices. So let me write it down. Is, let's say, singular or non-singular, if and only if I don't know, L prime, or let me call it BLC, which is the tuple BA1C, B, AM, C is singular, where B and C, GLN. So the matrices AI, you can think of them as linear operators. They act on f to the n. They act on f to the n on the left. They act on f to the n on the right. And I can change a basis. I can change a basis. I can change a basis on the left. I can change a basis on the right. This change of basis on the left and on the right does not change the character of whether the L is singular or non-singular. Okay. So it's pretty obvious, but one thing about it is it's really nice. And what's nice about it is that, this multiplying by any pair of matrices on the left and on the right is a group action. So we have a group acting on tuples of matrices which preserve the property we are interested in. Okay, and this is really good, because once you have this situation, the object or the property of the object you care about is preserved under a set of symmetries, then you can use the tools of invariant theory to study it, invariant theory and representation theory. This is the set of all invertible matrices over the field, okay? But it will be more convenient for me to just, it doesn't matter, I want to look only at matrices of determinant 1, so. doesn't matter for what we need, but it's more convenient from the invariant theory point of view. So this action of SLN squared on tuples of matrices is called, I don't know, sometimes it's called the left-right action. It's to distinguish it from another natural action, maybe even more natural action of just one invertible matrix where you just conjugate this set of matrices. You multiply, pre and post multiply by a matrix and its inverse. This is even a more well-studied action and a lot more about it. But we have this left-right action and it preserves the property we want. And it turns out, I'll soon make the required definition, is that another equivalent condition to singularity is that this tuple A1 AM is in the null cone of the left-right action. And this is a buzzword from invariant theory, which I'm not now going to define. So, questions so far? Okay. So now we want to So, in general, you have in invariant theory, you have some group G and some maybe X, it's just a set, and you have maybe I'll call it omega. X on omega just means that the group action, so what Gx on omega, so for every G in G, G maps elements of omega to omega, G in G, and we have it commutes with the group multiplication, GH of any omega, e.g. Okay. And so this is a general definition. It's just a group of symmetries. It's like, I don't know, taking, for example, you can take this pentagon and you can have rotation under, the group of rotations in, C5. Rotation by, how many? 72 degrees preserves this pentagon. So you can label it, and then 1, 2, 3, 4, 5, and the group of symmetries sends it to the relabeled pentagon. There are lots of examples where this happens. I want to tell you, so once you have this, there are two natural generalizations that people studying symmetries or invariant theory make. First of all, this set omega may have no structure, but you can immediately look at actions on its on all functions on omega. So you think of if this is the size of this omega is k, and there you have some field f, then you can think of this action as actually an action on, so Gx actually acts on f to the k. Right? It just permutes the coordinates. It just acts. I mean, omega is what's labeling the coordinates of the vector. So once you have an action on the set, you immediately have an action on a vector space. That's one generalization that's used. So this will be set V, vector space V. So G acts on V. And that's one thing which is studied. It's very important in representation theory. You are trying to decompose this action. Anyway, I'm not going to talk about this. It's a very important direction. you want to understand, to really understand this action, you really need to decompose the action on this vector space to its irreducible components. That's representation theory. In invariant theory, there is another generalization, further generalization that is made once you have this action on this vector space with these coordinates. You can think of these k components as variables. Let me give them another name. So here we will have k variables, z1, z2, zk. I have to stress because I keep changing commutative and non-commutative. Invariant theory, everything I'll say here is commutative, and this guy is commute. These variables. These k variables. Okay, so there is an action on the vector space, and because the vector space is indexed, can be viewed as indexed by these variables, which you can think of as names to the elements of omega. You can also think of G as acting on polynomials in these variables. They just permute the variables. So,
can you give an example?
yeah, I'm giving an example in a second. Yeah, I'm just, yeah. So you don't have to understand it. You'll see it all in action. Yeah, I want to give an example, but I have to say a few general words. Yes, I gave this example. But it's not. I want to give an example, but just 1 second. One more abstract nonsense. Okay, so I want to tell you what happens when G acts on f of v, which is just f of z1, zk. This is just so that's as usual, the polynomials, call it in over the field. So how is the action on this polynomial? Just by, whatever action it has on f sub k. And we will only look at, from now on, we will only look at G, which are linear groups. So just matrices. So you can think of G as simply as a group of k by k matrices. Permutes the variable. So now let me start showing you examples, and you will see how it fits in the. You all have seen this many times, but not in this generality. And we will build some intuition. I want to make one more definition here. So G will act on a set of polynomials. We'll see in a second exactly how. I mean, it's the obvious action. But if these are linear groups, they just change basis. So they will send Z1 will get some, L1 of Z1. That's what a matrix does. It's just think of it as a vector. And so the matrix, a group element, sends you just make a linear transformation on the variables that are the variables in your polynomial. And what I want to define is the polynomials that are invariant under the action. And this is what I'll start showing you examples of. So Fv, this set of polynomials, we look at a subset of it, so the invariant polynomials under the group action is just a set of all polynomials p in these variables, so that Gp is p for every g in G. All polynomials that don't change under this action. So let's start seeing examples. example 1. G is Sk. Okay? Now let me call it Sn. I mean, K will have different values. But let's say, so Sn, they got just a symmetric group. Symmetric group act on, so K equals N. And the group just permutes the elements. So now, clearly, if we have a polynomial, P of Z1 up to Zn, and we apply some permutation, I don't know, let's say pi in Sn, to this polynomial, it just, will be the polynomial P on x pi of 1. Sorry, Z. So the group action is clear, right? The way a group permutation acts on polynomials in n-variables is clear. Just permute the variables. Right? If pi is the cycle 1, 2, 3, and I have a polynomial, just a second, and P is x1, x2 plus x3, then pi P is x2, x3 plus x1.
So this was the definition.
That's the definition. Right? So it just changes the names of the variables. Here it's not even linear transformation, it's just a permutation. Okay, very good. So now here's my challenge to you. What is, in this example, what are the polynomials which are invariant under the action of the symmetric group?
Like some linear combination of symmetric.
You actually have a name for them. Symmetric polynomials. These are the symmetric polynomials. Yeah, I mean, just polynomials that look the same if you permute the names of the variables. So this is not a symmetric polynomial, right? Because when we apply some permutation to it, we get another polynomial. But on the other hand, here let me give you some symmetric polynomials which actually are a generating set for it. So I claim
Is it clear what GP is?
G, where?
When you write there G.
Here?
Here you define GP.
Yeah, so GP, yeah, so G is a matrix. I said we are looking only at matrix groups.
So little g times p.
Yeah, so little g times p is what happens when you apply, so
Here you just defined GP to be something specific, the pi p to be something specific.
that's right. And in general, if G is a matrix and Z is a bunch of variables, so you just think, so G is this. This is G, and here you apply it to the vector Z1 up to Zk. And you get another matrix, L1 of Z. And this is what you plug in your polynomial.
So you didn't really have to define pi p.
I didn't have to define pi p, but you can think of it as pi as a permutation matrix, right? So this is a special case of this, where the G's are permutation matrices. So I wrote it like this, but I could have written it like this. And when I apply it to Z1, Z2, Z3, again I forgot that I'm using Z's, I would get that.
Okay, so you don't need like a new definition.
I don't need a new definition, it's just sometimes
Okay, you
people
just
call.
simplified it here, right?
Yeah, I simplified it so it will look familiar. Yes.
But this is the FVG.
Yeah, FVG is just this is invariant polynomials. And in every group action, they will be different. Okay? So I'm giving you the simplest example of invariant polynomials because everybody...
Hence invariant theory.
Hence invariant theory. They are invariant, they do not change under the group action. You apply any group element to this polynomial, it stays the same. It's invariant. So, what are these? This is the first elementary symmetric polynomial, right? The sum. The second symmetric is the sum of products of pairs. The third, the sum of products of triples, blah, blah, blah. And the last one is the product. Okay? So I want you to notice two things. First of all, there are infinitely many symmetric polynomials of any degree, right? However, all of them are generated as an algebra by very few polynomials. Once we know these, we know all the others. Okay, how do we know all the others? Every element here is a polynomial in these polynomials. This is what generated as an algebra or as a ring means.
So
Every polynomial.
this will always happen?
This will always happen. So, well, I didn't say it yet that it will always. I didn't say that it, so I didn't say that it always happens yet. I will say that it always happens. But in this example, if P is any symmetric polynomial here, then it means that there exists some Q of, I don't know, alpha 1, alpha n, such that P will be identical to Q when you substitute in it the polynomial sigma 1 to sigma n. That every symmetric polynomial is some arbitrary polynomial in the elementary symmetric polynomials here. So this is a generating set, and generating in the sense of algebra, not of linear algebra. Right. So any symmetric polynomial is a polynomial in the elementary symmetric ones. So this is one basis or one generating set for the elementary symmetric polynomials. You all know that you can take other, right? You can take here the traces t1, t2, tn, where this will be still the sum of the zi, but this will be the sum of the zi to the n. So it's just the sums of powers also happen to generate the elementary symmetric polynomials. So this is the main object of study of invariant theory. These invariant polynomials, and usually they talk about the first fundamental theorem and the second fundamental theorem. The first fundamental theorem is just identifying in some way, symmetric polynomials have a very simple description. Sometimes it's not so simple. So this is the first fundamental theorem.
So what is the theorem?
Theorem is that I know I'm describing to you all the invariant polynomials.
For every g?
No, for each particular g, the first challenge is identifying all the invariant polynomials. Here it's easy, we know them.
You're saying that for every g there are two theorems? One
Usually, yeah. So there are two theorems. First, you want to identify what the hell are all the invariant polynomials. You identified it, you prove the first fundamental theorem for this g. Great. Yes, and then you want to give a set of generators for it, and that's harder. That's the second fundamental theorem, set of generators for it, and moreover, you want to understand the relations, the algebraic relations between the generating polynomials. What are the algebraic relations between these polynomials? There are none. They are they're algebraically independent. You mean tricky question? So this I wrote this example because this is the ultimate. This is what everybody would want for every. This is the second fundamental theorem. So they actually write these acronyms: FFT and SFT. SFT is basically when you have a generating finite generating set of polynomials, and actually you know the relationship between them, and in this case you know because they are algebraically independent.
This will always be finite?
Well, that's a good question. Let's see. Before we see, let me give you another example. I want to tell you here, notice that it's not only finite, it's the highest degree. If it's finite, it means there is a degree upper bound on all the generating polynomials, and indeed there is a degree upper bound here, it's n, and this is the same, let's say, dimension of the group. Okay, so it's polynomial, it's linear in the dimension of the group. Here's another, okay, so this is a good example. Here's another question, another example. Another example, so which you also know. So let me now go back to SLN. So G is SLN squared like before, but the variables we act on are these. Z11, Zn, so k equals n squared. And the action is multiplication by the left and by the right. So matrix Z like this. So B and C in this group map a matrix Z to B, C, C.
Are you indicating that Z is diagonal?
No, there are Z11 to Z, sorry. Thanks, yeah, that wasn't clear. It's n squared variables. So there is a group action, right? Multiplying by the pre and post multiplying by constant matrices makes a linear change of these variables. Okay. Can you think of a polynomial in these n squared variables that is preserved under this action for every B and C? Right? B and C are elements of our group. Determinant is good, yes? Determinant. Okay, so good. So we are trying to understand as before if the invariant polynomials and definitely this is preserved, right? The determinant, these are matrices of determinant 1. So it doesn't matter what they change, they don't change the determinant. What else? Hmm? No one else. This is the only invariant. So, okay, of course, polynomials, the powers of the determinant are fine. So that.
Explain how this is the G times the C. Like, how does this fit the definition of every G?
Well, you have to write, yeah. So if you write Z11 up to Znn as a vector, then I can build for you for every B and C. I can build for you a matrix GBC, which will tell you what it does to the variables, obviously. Because it's linear, right? I mean, you multiply by constants on the left and on the right. I'm not going to do this. You can do it for fun at home. Yes. No, but you agree that this can be done. It's just this is a concise way to represent that. Okay. Good. So again, a full understanding of the invariant ring of polynomials. It's generated by one element of degree n in this n squared variables. Of course, there are no relations. There is only one generator. So this is exactly the type of understanding we aspire to. And the last example will be just the example we care about. Just generalize this from one action on one matrix to action on tuple of matrices. So now, what we want is G is the same SLN2, but now it acts on K's m times n squared variables, which are arranged in matrices Z1, Z2, Zm of n by n matrices, and they are mapped under a pair BC from here into what we saw before, BZ1C. Okay, So it's again a linear action on the variables. You can ask the same question. What are the invariant polynomials here? I don't expect you to guess, although the answer is on the board, so maybe you can guess. What is f? G in this case, this is a theorem by several people proved it around the year 2000. Schofield, Field, and Van der Berg. Domokos, and Zubkov, and I think another group characterized the invariant polynomials for this action. They proved the first fundamental theorem. So this thing is for every d, well, you can look there, you can pick there if you want, it's the same. For every d, and we have this, what I called xi's there. These are symbolic matrices which are n by n, determinant of the sum. D by d matrices, so xi and so di. In fact, I can write it. Okay. The invariant polynomials, this is an infinite generating set, unfortunately. But it says that if you want to know what are maybe I should have, sorry, let me fix this. To use the mi. This is over characteristics 0 fields. So again, if you want to know the invariant polynomials of this group action on tuples of matrices, here's a bunch of pretty obviously invariant polynomials. It's clear that these polynomials, I mean, you should think about it just a minute to convince yourself that if you, that this particular group action is not going to change these determinants. Okay, it's easy to see, and what is harder to see is that these are all of them. All of them are generated by these matrices. So this gives us a connection. So here, invariant theory comes to, and supplies exactly the same condition for singularity. These are the invariant, these are exactly the invariant polynomials under this action. And what I wrote here, this null cone, is just one important thing that is people in invariant theory are trying to understand is not just what the invariant polynomials are, but what are the objects that under the invariant action, under the group action, are zero of every invariant polynomial. So the null cone theory is another definition. It will not be important for us, but just the null cone is all tuples, all values that you can think about here, all values to the variables. So maybe 1 alpha k, such that p of alpha is 0 for every invariant polynomial. And this just fits what we said here. We said that these determinants here, the determinants of these constant matrices are 0 for every substitution of matrices M for every size.
What do the alpha i's here?
The alpha i's are in F. In F, yeah. So that's the general definition. If you want to think about it here, these are values you give to the A's. Remember the Z's were, I for a good reason, separated the X variables which are here and the Z variables which are there. When you give values to the Z variables, this is like specifying a set of matrices AI, and we get it to be vanishing on all these polynomials exactly when the AIs are a singular symbolic matrix, represent a singular symbolic matrix.
In example 2, the determinant is not changing.
Determinant?
The zeros.
You agree that
Zero,
let me note here that the determinant
that's
of BZC is the determinant of B times the determinant of Z times the determinant of C, and these are both 1 by definition,
Oh, okay. Okay.
right? Yeah.
So this is kind of idiotic, really. But when you define your invariant theory, you made a point of saying the variables that go kind of build your polynomials.
Yeah.
Well, this is all tangled up with this weird commutativity, non-commutativity situation.
Mhm.
You said that we're going to assume that the variables are commutative.
The variables ZIs, they are
Yeah,
always
I mean, that's
commuting.
the way invariant theory is.
That's right.
On the other hand, so I was wondering as you're doing this, why they did that, given the fact that there is some richness to assuming you don't have it.
Yeah, so
If you assume, I think, that variables, you just play the same game you just did. Like, do example 1, where you assume the variables don't commute. Then, I mean, a set of invariant polynomials are completely trivial. They're probably only linear, the symmetrical linear polynomial. I mean, the thing is, the theory kind of degenerates into some very...
in this
That gets to your
case,
Yeah, in this case.
in this case.
That also gets to your original point that when you throw in non-commutativity, it would seem to me non-commutativity is a hell of a lot more complicated than commutativity.
Not always.
Yeah, I mean, just there.
That's right.
Because the non-commutativity forces all these parallel things to have to be trivial, so that it makes. I mean, it's just kind of a weird thing.
So you can do it, and some people do this. I don't want to do it because to me, in this picture, the Z's are always commuting, and what's non-commuting is their coefficients, the X's, right? These guys, which here they were commuting, and to make them non-commuting, I make them matrices of, large matrices from, yeah. But anyway, so I don't want to. You can do that, and I think the message is which is more complex and which is more simple is a good question. Sometimes, well, it depends what you want, and sometimes non-commutativity is simpler. It's certainly easier to prove lower bounds for non-commutative circuits than it is for commutative circuits. So I just want to get to this point. I'll take a break in just 1 minute. I want to tell you what is known about this is the first fundamental theorem. We have we understand what are the invariant polynomials. Let me tell you about the finite generating set. So much less is known. So we are still with example 3 now. What is known about the finite generating set here? A second fundamental theorem. And this is okay, so first of all, I want to say something more general, what Gilad asked before. Is there always a finite generating set? It's not clear. It's not obvious. And this is a theorem of Hilbert from 1890. And you all know this paper. I mean, in the sense that this is a paper which has in it the Null-Zahlen-Satz. This is a paper which has in it the finite basis theorem. It's an amazing paper in the history of mathematics. And he developed all this machinery for one purpose. I mean, then it found many other purposes. He developed it in order to understand invariant theory and finite generating sets for, second fundamental theorem. And what he said is that So this is for all reductive group G, which reductive doesn't matter what it is, but it contains all the linear matrices, all subgroups of groups of matrices. For all reductive groups, the invariant polynomial is finitely generated. It's always generated by a finite number of polynomials. So in particular, when it's finitely generated, it means that there is some upper bound on the maximum degree of a polynomial which appears in this finite generation, which is exactly what we want to understand. What is the degree upper bound? So he didn't give any degree upper bound. I mean, for those who know the story, he was young at the time, he got a lot of bashing from the mathematical community. People call this paper a paper in theology as opposed to a paper in mathematics, because he proved it in a very non-constructive way. There were lots of complaints, and he wrote another paper which was slightly more constructive, but still didn't provide any upper bounds. And then a series of people started working on upper bound, and the important one for us was Dirksen, around 10 years ago, proved that d of n, so d of n is, again, here we define d of n in this way, but d of n is an upper bound on the degree of generating invariant. So Dirksen proved that this is at most exponential in n squared. And it is this bound that I will use after the break in order to give you an analysis, the polynomial time algorithm for singularity. Okay, it's this bound. This happened 10 years ago. A month after we wrote our paper, and the development that led to the improved theorem, which I erased already, was that the same guy, Dirksen, and his postdoc, Makam, proved d of n. We proved the polynomial upper bound.
And this is for every...
This is over characteristic 0, but then later, I guess the proof for general is Ivanov-Skiao and Ivanov-Skiao with the bound for every field. Or maybe that, every large enough field. No, maybe it follows,
So
yeah.
the degree bound has to be only for Dirksen, and it's only for algebraically closed fields.
That's the original one, but this one.
But if you want to find the degree generators, then you rely on the theorem of Dirksen. That only works for...
Yeah, that's right. Okay, that's right.
But is this just, for example, 3 or for every?
For 3? No, for 3, yeah. It's not just for example 3. If you want to know I'm not going to write anything down, but the world in which this lives in, how general this is an action on a tuple of matrices. There's a more general family of actions called quiver representation, where quiver, what is a quiver? Everybody knows, so Lord of the Ring, this guy with a quiver of arrows on his... So quiver is a collection of arrows. What would mathematicians call a collection of arrows?
Bundle?
No, that's another particular collection of arrows. No, a directed graph is a quiver. So a quiver is a directed graph. If you want to go look at very nice. I really like it. Anyway, we have this upper bound, and let's take a 5-minute break, and then we'll use... I'll tell you the algorithm, I'll tell you how this is used in the analysis of the algorithm, and despite the fact that this is exponential, it will lead to a polynomial time.
What's the difference between this upper bound and the second one?
That's a polynomial upper bound.
Yeah, but why are you going to use this?
No, it's just that we didn't know this. This is sufficient for us. The analysis doesn't change if you give me a better bound. It works as long as this is exponential. It works even better. I mean, it works the same way if it's polynomial. It just doesn't help. Somehow, polynomial is the right, exponential is the right bound.
Does this mean you can just terminate this generating side of
Yeah, exactly. So if you take all of these polynomials that are written here, such that d is at most this or this, then you generate all the others. It's not obvious. Yeah. Okay, break. And one of them is what's called that L is rank decreasing. Rank decreasing, it shrinks, so it has a shrunk subspace. Sometimes it's called shrunk subspace. Or rank decreasing is you want that there will exist, so it's singular if there exist two subspaces in F to the end. Dimension of W is smaller, strictly smaller than the dimension of U, so that every one of these AI, and therefore every one in the linear span, sends U to W, so that for all I, AIU is contained in W. Okay, you somehow send, all these matrices send U to W. So in particular, the rank decreases, right, because the dimension of U is smaller than the dimension of W is smaller than the dimension of U, and it's clear that if this is the case, all these matrices are singular. I mean, they lose in the rank at least one. Okay, so it's clear that if this is the case, then L is singular. What is not clear is that if it's singular, this holds, and that's another important theorem of Kohn. That is equivalent to the other definitions.
Is there an analog in commute?
Very good question. This is just a sufficient condition. It's not if and only if in the commutative case. It's just not if and only if. Certainly, if this happens, the rank itself also is. So I didn't write it here, but it's clear. So it's something I probably am not going to get to. So let me write it here as a commutative rank is always at most a non-commutative rank. Okay, and therefore, if you have this, the non-commutative rank is not full, and so the commutative rank is also not full. But it's only one direction. Here it's a characterization of having a non-full, non-commutative rank, and in the commutative case, we don't know a characterization of this type. And it turns out this is a theorem of 14, not hard, and Rettenauer. Actually, it follows from a lemma of Flanders, that is at most twice the commutative rank. So, because of this, we know that since we can determine a polynomial times the non-commutative rank, we have a factor 2 approximation to the commutative rank. And it's a really nice open problem. Find the p time 1 plus epsilon approx to the commutative rank. You can do 2, improve it. So that's a very different angle on the polynomial identity testing question. You're not trying to do it for, things that are easily computable. You are trying to do it for, you are trying to do something else. Another question that comes out of this is trying to do polynomial identity testing, not for polynomials that are computed by various types of restricted circuits, but solving it for families of matrices L, which have some structural requirements, some structural limitations, as opposed to computational limitations. And this leads me directly to Gurvits' paper. So I want to tell you about Gurvits. 04. But actually, before this, I just want to mention, last week we had a lecture by Steve Fenner and this work of Fenner, Gurjar, and Tieruf do the commutative PIT for L, which in which you can think of them as the read ones. Every entry is either some xij in position I and j or 0. That's the perfect matching question, right? So we know that this can be done in, well, quasi-polynomial time. That's exactly what he did in this language. He didn't state it like this, but that's... So you can ask, what other matrices of some special form can you do? For example, if you allow arbitrary constants from the field and distinct variables, does it work? We don't know. And what Gurvits did, he gave a polynomial time algorithm for singular for L, such that the commutative rank of L equals the non-commutative rank of L. So he had another restriction on linear, on symbolic matrices, those matrices for which the commutative and the non-commutative rank are the same. Such spaces have a name. They are called compression spaces. They arise in various linear algebra studies. The name comes from a paper of algebraic geometries on bundles of Eisenbad and Harris. So there are motivations for studying this kind of spaces in various areas of mathematics. And Gurvits actually makes a point of saying that they arise quite, they arise all over the place. He gives some examples of compression spaces. For example, the spaces generated by the following types of generators. So the AIs, if you have AIs generating your space L, which are, for example, PSD, or which are, for example, upper triangular, generated by A1, AM. If all your AIs are PSD, then it happens that the space they generate is a compression space. So it satisfies this condition. Therefore, Gurvits' algorithm actually solves the problem, tells you whether it's full rank or not. Of course, here the rank is the same in both. Upper triangular the same, and the most non-trivial example is where all the generators are rank 1. This is a hard thing, and it follows from the duality theorem for matroid intersection, the Edmonds-Rado theorem, for those who know. Doesn't matter if not. Turns out that also in this case, you have a compression space. So I want to tell you what Gurvits' algorithm is. It turns out that Gurvits' algorithm is the same algorithm we are going to use, only we are going to show that it solves the problem not only in this case. It simply, computes the non-commutative rank. It tells you whether it's full or not. Okay. And I'll tell you what he missed. In fact, he missed the invariant theory, the connection and bounds. And once you know it, it's pretty simple. Okay, so I want to tell you, so now we are moving to a different analogy between the commutative and non-commutative setting, because Gurvits' algorithm, let me write it here, algorithm G, this Gurvits algorithm is a quantum analog, so a non-commutative analog of an algorithm that I'll call S. It was developed by Singhorn in the 60s for purposes of numerical analysis and stability of linear systems. And we used it and analyzed it in an analysis that Gurvits is generalizing in a paper with linear Samorodnitsky. In, I think, 2002. So a year or two before Gurvits' paper. So I want to tell you about this, and I want to explain the analogy to the algorithm of Gurvits, and the algorithm that will eventually solve our problem. And so I said this is classical and that is quantum. And I already made this joke in the Monday seminar that Peter was unhappy with, saying that there is a very simple way to move from classical to quantum. You just take diagonal matrices to general matrices and you move from L1 to L2. But that's exactly what we'll do here, or what Gurvits does. And well, it does more than that. So let me tell you about synchronous algorithm. In synchronous algorithm, so here we know the input is a tuple of matrices, A1, AM, maybe tuple of rational or complex matrices. Here the input is just one matrix, A, and in fact it's a positive matrix. And so Aij is non-zero, so the entries are non-zero. Here, as we'll see, I'll define it in a second, this will also be positive in a sense. This will be a completely positive map. So it will also be positive in a way that generalizes this positivity to the quantum setting. So what was Synchron trying to do? He was looking at matrices like this, non-negative matrices, and asked whether you can make them doubly stochastic. Okay, so you have a matrix A, non-negative matrix, and you want to make it doubly stochastic. Now, what are you allowed to do? What you are allowed to do is to pre- and post-multiply it by diagonal matrices. Namely, another way to think about it is scale the rows, so multiply the rows by constants, multiply the columns by constants, and after that you want the row sums and column sums to be. So here you have some matrix B, here you have some matrix C, and what you want is that diagonal. You want that BAC is doubly stochastic. Now, it's not always possible to make a matrix doubly stochastic. For example, if there is a row of zeros here, there's nothing you can do to make the row sums 1. There is a column of zeros, same problem. In fact, there are more general limitations. For example, if you look at this, this matrix turns out you cannot make doubly stochastic in this way. So, well, what would be the condition that will ensure that we can make it doubly stochastic? Non-singular is not enough. But you're close. The permanent should be non-zero. It should have a diagonal. It should have a non-zero diagonal. So it turns out that this is possible, so there exists B and C, which makes it's easy. It follows from Hall's theorem. In fact, this here you see a whole block. Right, there's a set which is, well, there is no perfect matching in this graph because of Hall's theorem, for example. It's the same condition. It's not hard, but I have to change it. I have to change it from doubly stochastic to almost.
But why do we need a matching?
We don't, but that's a connection. I'll define it in a second. We don't know, it happened. So we don't need a matching. We want doubly stochastic. That's what he wanted, Synchron. It turns out that you can do it if and only if the permanent is positive. And that connects it to the permanent, which is what we studied here. We wanted to develop an algorithm for, deterministic algorithm for approximating the matrix of a non-negative matrix. So that's the connection. We in fact discovered synchron algorithm, and we rediscovered, but then it was known. But the analysis we had is different, and I want to tell you the analysis.
So is that more consistency?
Yeah, so exactly. It will tell us, yeah, so I didn't define an algorithm yet, but I'm going to. But I first want to tell you what do I mean by almost. Almost I mean that you can, in some matrices, so this is, you cannot make doubly stochastic, but this, let's say 1, 1, 1, 0, you also cannot make doubly stochastic, but you can make it almost doubly stochastic. So first note that here the permanent is 0, there is a diagonal. But as you keep multiplying it by things, you can, let's say, multiply this by, I don't know, epsilon, 1 over epsilon, 1 over epsilon. Right, and this will give you 1, 1, epsilon squared, and 0. Right, so you can make it as close as you want to. So what you want, so almost means that you have, for every epsilon, there exist matrices. So that B epsilon A, C epsilon, this B epsilon A, C epsilon minus, when you compare them to the doubly stochastic matrices in any norm you want, the row sums, the column sums, you know, this is in any norm, it doesn't really matter. L1 at infinity. So you want to converge to a doubly stochastic matrix. Okay? That's what you want to do, and this is possible if and only if the permanent is positive. Okay. So let me tell you how this is done. Okay, so we want to make it doubly stochastic, which means row stochastic and column stochastic. So let me make the following notation. It's pretty obvious if you want to make a row stochastic, what you would do, which diagonal matrix you will multiply. You will look at every row sum and divide by it, right? So let me denote row of A, the diagonal matrix, which is 1 over row I. Ri is this row sum. Okay, this is R of A. And here, and similarly, I want to denote the C of A is the diagonal matrix with 1 over the column. Okay? And you've seen it before. Those of you who were here last Monday saw it, but I'll write here algorithm S, synchronous algorithm, repeat n cubed times. A multiplied on the left by row of A. So normalize the rows. This creates another matrix where the row sums are 1. Maybe the column sums are not 1. No problem. You again change it by multiply it from the right. This creates a matrix whose columns are all 1s, but maybe the rows are not good. And then you repeat it. So you repeat. And at the end, you want to test how close it is to being doubly stochastic. So let's say the last thing you did is normalize the rows. You can test the distance of, I don't know, the row sums of the vector. So here the columns are normalized, so the rows, so row sums are n minus the all ones vector. Let's say L infinity. Test whether this is 1 over n or not. Okay? And you just say, and so if this is true, then you say yes, permanent of A is greater than 0, and if it's bigger than 1 over n, you say permanent A equals 0. So notice, this is an algorithm for perfect matching. It tests whether the permanent is positive or not. It's just an algorithm for perfect matching. It's the easiest algorithm to code for perfect matching. Just start from the adjacency matrix and just apply this. It's 2 lines of code. Okay. So why does it work? So I want to tell you the analysis of this. The algorithm is clear? Okay. How would you analyze this? So you need, it makes sense at least to have some progress measure on the algorithm. You want to say that something, so this is a dynamical process on you start with A, which is A0, your original matrix, and then you generate a sequence of matrices by these 2 steps. And we want to say that in polynomial number of steps, if you didn't come very close to doubly stochastic, you will never come close to doubly stochastic. Okay? We already know that, let me do the analysis. So what's the analysis? This is from our paper with Lineal and Samrodnitsky. The progress measure is going to be the permanent. So we will have a mu AI, which will be the permanent of AI, and later we'll look at more general news, which is what Gurvits does. Okay? So what can we know? There are 3 properties that are important for the analysis of the convergence algorithm. So first of all, let's say we start with either row stochastic or doubly stochastic or column stochastic A without loss of generality, and then we know that the permanent, so let me write it here with mu of AI for all I okay, because the permanent of a matrix is at most the product of the row sums of the matrix. Yeah? It's very easy to observe. That's one thing. The second thing that is important. So let me now, so let's assume that the AIJs are bounded by, they are integers and the number of bits in this integer is b, then it's not hard to, or rational numbers that can be represented by b-bit integers, that mu of A0 is at least exponentially small. Maybe anyway, it's very simple to see. So you have a lower bound. And so all we need to do is to show that every step of the way makes us closer to 1, and we cannot bypass 1. So either we get arbitrarily close to 1, where
Why do you need exponential? Why not just
because we want polynomial time convergence. Because we want polynomial time.
steps?
If it's just arbitrarily, if it's just positive, how do you bound the number of steps? So let me write the third condition.
You assume that A is not with permanent 0, right?
Yeah, A is not with, so if it's permanent 0, then it gets stuck.
So exponentially small in what? In minus what?
The number of, the size of the matrix and the number of bits in the representation. Think of, the entries as rational numbers with b-bit integers describing them. And this 1 plus 1 over n, the permanent of AI. And this is as long as AI minus the doubly stochastic matrices is big.
Yeah, so it's multiple. It's not additive.
It's multiplicative. Yeah. That's now I understand what you are. Sorry. It's multiplicative, and it has to be multiplicative because we want 0 not to change. Yes. That's right. So it's multiplicative, and of course this already gives you polynomial time convergence. Right. So what is the analysis of this? It's extremely simple when this is a permanent. And in fact, as you'll see, it doesn't have to be the permanent. It just has to be something that's multiplicative in the determinant of these guys. The determinant is the product of the entries of these diagonal matrices, and of course the permanent changes exactly by this product. And if you had a matrix that's some permanent, and then you multiply every row by some constant, then the permanent becomes the original permanent times the product of these constants. So what do we know? So we know that the mu of AI plus 1 is exactly the product. Let's say, without loss of generality, we just did this, and now we are doing this. Okay, so we are changing it by one of the column sums of, these are the column sums of AI. Okay, maybe I should say J here. J. So these are the column sums of AI times the permanent of AI. And now the only thing to do when you have a product and you want an inequality is use AMGM inequality. So this product becomes a sum. What do we have? N, it's inverses, right? So it's n over the sum of Cj to the n and 0 of AI. And this is really nice because this is a sum of the column sums. The sum of all the column sums. But the sum of all the column sums is the same as the sum of all the row sums. And all the row sums are 1 because the previous step made all the row sums are 1. So this is 1. So we already know that this is at least mu of AI, which is the first step. It just shows that these permanents are not decreasing. But we wanted more. We wanted a factor here, right? And the factor we get because AMGM is tight, gives equality only when all the numbers you care about are the same, which would be 1. But we said they are not because we have this gap, and you can calculate to see that this gives you something. Okay, so this is it. That's the analysis in the classical case. That gives a polynomial time algorithm.
But now we didn't need any bound on D or anything like that.
No, nothing. There is no D. Yeah. There is nothing like D. Okay, now I want to do the D is coming soon. See how much I managed to do, but okay. So what is Gurvits' ingenious connection? He actually, the paper has a lot of things. I mean, what he really wants to do is to solve the commutative identity testing problem. We cannot do it. It does it only for spaces which are compression spaces. But the connection he uses is this shrunk subspace, and another characterization which he adds to it, that a space is singular if and only if, so this is in the non-commutative setting in general, you have this condition if and only if A1 up to AM viewed as a completely positive map. So this completely positive map, which I'll define, map is rank decreasing. And rank decreasing is exactly this condition. Has a shrunk subspace. So he proves that these two are equivalent. And now I have to tell you what completely positive map is and how this connects to, how this problem connects to this problem. So what's a completely positive map? You can view this in quantum information theory. They have this notion of a completely positive map, A1 through AM, which sends, so this, let me call it L again. So L of P is also an n by n matrix. N by n matrix. It sends the matrix P to the following matrix, AI, P, AI dagger. Dagger is the conjugate transpose. Okay, so if the AIs are complex matrices, then you send P to this set of matrices, to this sum. So it takes n by n matrices to n by n matrices. What's the positivity here? Positivity is pretty obvious. If in this map, notice that if P is PSD, then this L of P is also. And they care about it because they are going to apply in quantum information theory. This operator is sometimes called the noise operator, sometimes it's called the general quantum operation. And they care to apply these quantum operations or noise operators to general quantum states, which are density matrices. What are density matrices? They are simply PSD matrices that also have trace of P is 1. And if you care about this, then you also care about the maps which preserve the trace. And they preserve the trace if, so L is called, this completely positive map is called trace preserving if L of I, which notice that this is just the sum of AI dagger, right? Is the identity. So in this case, L is called trace preserving. And for us, or for Gurvits, this trace preserving is exactly row stochastic. This is the analog of row. So if you wonder in the analogy between classical and quantum, where from a matrix A, I mean, how is this a special case of this? This is a special case of this if you take the matrix A and convert it to n diagonal matrices whose diagonals are the different rows. Okay, so you can make from this n matrices, they are diagonal matrices, which are the original rows of A, and put it here. This will make it a completely positive map. When you write the rows on the diagonal and you have n of these, this will special. So everything I will say here, if you want to find this there, that's how you find it, through this map, through this conversion of A to a bunch of diagonal matrices. So this is really a quantum generalization of this, and in fact the algorithm and the analysis will be a generalization. So let me tell you just one more thing. So if this is row stochastic, what is column stochastic? Column stochastic arises from the dual of this completely positive map. What's the dual? So L star of P is what happens when you replace A and A transpose. So this is the sum of AI dagger PAI. Okay, and here, if L of P, L star of P, of I, sorry, I is I, then this is the column stochastic. L star is preserving trace, and this is column stochastic. And now what is doubly stochastic? Both L and L star, when applied to the identity matrix, give you the identity matrix. And what Gurvits show is that in this case, the rank cannot decrease. It just is in the same way that a matrix here, which permanent is, maybe I should have said it before, a matrix A whose permanent is positive will never have a subspace, will never shrink, will never have a shrunk subspace. Because in particular, well, if the diagonal is actually the main diagonal, and you can get it by permuting the columns, if the diagonal is the main diagonal, then the image of U will in particular contain U. So what it proves is that the same as here. So L is not rank decreasing, if it can be scaled, like here, it can be scaled to be doubly stochastic, or really almost doubly stochastic, just exactly the same. So not rank decreasing, if and only if, and I am mentioning here that this is if and only if L is non-singular, non-commutative, non-singular. If and only if there exists B and C, again, GLN, invertible matrices, such that, well, maybe for every epsilon, B epsilon, C epsilon, such that B epsilon L, C epsilon. So you just do the same to all matrices, right? Minus the quantum doubly stochastic, maybe I should say quantum doubly stochastic are those that are both column stochastic and row stochastic, right? Okay, if you can make them as close as you want to doubly stochastic matrices. So we are faced with exactly the same question. And moreover, once you're faced with this question, you realize, it's easy to realize, that you should apply the same algorithm. Let's see. I mean, if this condition doesn't hold, if L of I is something else, well, if it's not an invertible matrix, then it will never be, it will never, you know, it will be rank decreasing, just like if you have a row of zeros in the classical case, you can never have a positive permanent. So when this is some invertible matrix, you multiply it by, not its inverse, but it's this, like the diagonal here was the inverse. We need the square root of the inverse because in the operator we have A appearing twice on the left and on the right. Okay, good. So what? No, does not compute the permanent. It just changes the permanent in predictable ways, right? It just, the permanent of the first matrix will be the permanent of the last matrix times the product of all these factors that you changed it by. Okay? That's exactly what's serving us in that paper in order to approximate the permanent.
So you know the changes that you made?
Yeah, you know the changes that you made because you compute them. They are just row sums and column sums. So you can deduce the ratio between the original and the final permanent. And I can tell you.
Permanent is easy?
Yeah, exactly. So, and then it's not easy, but when you eventually get to a doubly stochastic, yeah, then you know something. What do you know for doubly stochastic matrix? The upper bound is at most 1. What?
Okay, yeah.
And the lower bound, you want an approximation, so you want to use some theorem about, yeah. So at least you reduce it to a structured case. And in the structured case, in doubly stochastic matrices, there is a van der Waals conjecture, which was proved by Gurvits and Olivera, that tells you, well, obviously the upper bound is most 1, and the lower bound, how would you minimize the permanent of a doubly stochastic matrix? The conjecture was, and that became a theorem, is that you do it in the most obvious way. You fill a matrix with the numbers 1 over n. This will make the permanent as small as you. Yeah, actually, it's a very difficult theorem. The original proof uses convex geometry and some heavy-duty machinery. And about 10 years ago, Gurvits found a very different proof using stable polynomials, which inspired, for those of you who know, Marcus Spielmann-Srivastava paper on Cadison-Zinger and on Ramanujan graph, so who also use stable polynomials. So Gurvits has a beautiful proof of this van der Waals conjecture, and actually of a much stronger conjecture of Scriver. It's a very important, beautiful paper. So, but this was digressing. I want to tell you what the algorithm of Gurvits is. Okay. So, like before, you repeat. Well, maybe I should put B here. So we said if we don't get, if you don't get, when we apply L to the identity matrix, we don't get the identity, we have to scale it. So A gets L of I. So it's some other matrix. Notice that it's always positive definite. So we can take square root and inverse times A. And we alternate this and the column version. A times. So L of I, well, I should have probably, let me just make the same notation as there, so it will be nice. Rho of A, and now rho of A, here you see the L1 turning into L2. Rho of A is, rho of L, sorry, it's all L. L. Rho of L is L of I to the minus 1/2, and C of L is L star of I to the minus 1/2. Okay, so we either multiply it on the left by this normalizing factor, or we multiply it on the right by this normalizing factor. And one thing makes it rho stochastic, the other makes it cone stochastic. And then you test as before. Test the distance of L minus the quantum doubly stochastic matrices, whatever it means. Check whether it's 1 over n. And in this case, you say that it's not rank decreasing, so L is non-rank decreasing, which is the same as L is non-commutatively non-singular. If we can get to doubly stochastic, then it's not singular, and if it's bigger than 1 over n, then you say that it's rank decreasing, which means that L is singular. This is not Gurvits algorithm. This is Gurvits algorithm if you allow L, I mean if L is a compression space. And what we say is the same algorithm works. In fact, this condition, which is tested in Gurvits algorithm, tells you really whether it has full non-commutative rank or not. Okay, so the last 5 minutes, so the algorithm is clear. You can see that it's the exact analog of this algorithm. You scale rows and columns in this appropriate meaning of rows and columns. You scale, multiply either from the left or from the right by some matrix. Now it's not a diagonal matrix, it's either this matrix or this matrix, some matrix. And in every step you make it either row stochastic and cone stochastic, and this thing converges. So how do you prove that it converges and converges fast? I claim that the two of these three are really obvious, are exactly the same. I'm not going to do it, I'll tell you what they are. It's at most 1, if it's row stochastic, that it's at most 1. Okay, well, I didn't tell you, okay, I have to tell you what mu is. Okay, so let me tell you what mu is. And actually, Gurvits makes 2 suggestions. First, he suggests taking mu to be a quantum permanent, which he defines. Quantum permanent. It's something that, well, I can define it, but anyway, it's a polynomial that depends on the entries of all the matrices. And if you specialize it in a way I said, you build from a matrix, you build a family of matrices, then you get the original permanent. Anyway, it's a polynomial. It's always non-zero and so on. It's always non-negative and so on. That's one measure that is multiplicative under the action of this algorithm. And then he has just a second, Gilad. And then he has another one which is called capacity, which I'll define for you in a second. This I will define because it's important. Yeah.
So I find kind of weird. You want to know if the determinant is zero or not to solve singularity.
But it's not a determinant. It's not a determinant. It's something else. You really want to know this.
You want to know the determinant, and here you compute the permanent, and somehow it helps you. Like the analog of this.
Yeah, no, but also here you want to know the permanent, really. You want to, either know the permanent or control the permanent. You want to know positivity of the permanent. The analog of positivity of the permanent in the classical case is this, in the quantum case, that there is a shrunk subspace. This corresponds to the permanent being zero, somehow. It's not hard to show. This correspondence between this and this. But this is what you should think of. Let me tell you, maybe it will help if I tell you just a second, what's the connection between, so maybe I'll take a few minutes more. How is this related to the permanent being non-zero, this condition? Okay. Let me.
Conditions are about the determinant.
But it's a determinant with tensor products. It's not about, so it's something else. It's something else, and it's a deep theorem of Kohn that they are related to the shrunk subspace.
Somehow you have both the determinant and the permanent coming up in the singular.
Yeah, but the determinant comes up mainly in the scaling factors, in the factors by which we change the determinant, by which we change the permanent. Right? We multiply it by diagonal matrices or here by non-diagonal matrices. So it's just in how we control, we can relate some quantity in every element of the sequence to the element in the next. This is controlled by determinants. But the value we care about is something else. It's some property which should be multiplicative with the determinant. So the way it changes by a factor which is the determinant of the scaling matrix. Okay, but this measure, so these are the measures we talk about. It was permanent there, it will be either quantum permanent or so. But let me just tell you the connection in the classical and quantum case between the permanent. So here is the classical, and here the quantum, or really the non-commutative. So here we have a single matrix A, and I claim that the permanent of this is zero if and only if there is some permutation matrices B and C, permutation matrices, which will show you a block of zeros, a big block of zeros. That's the whole condition, right? So B, A, C looks like this. These are zeros, and it's too big in that if this is A and this is B, A plus B is less than N. The whole thing is N by N. So the block of zeros, the sum of dimensions bigger than N, this is a whole condition. You recognize it.
This is the witness for.
That's a witness for non-perfect matching. And here we want a witness for rank decreasing, which is non-doubly stochastable or whatever. And actually, it's a witness. It would be a witness for. Well, okay, we'll talk about capacity in a second. Here you want, so here A1, AM is rank decreasing or has a shrunk subspace. If and only if there exists exactly analogous condition, BC. Now they are just invertible matrices, GLN, such that B, LC, so B, if you want BAIC, all of them have exactly the same structure. All of them look like this, exactly the same. And you can find here exactly the subspaces U and V that are, right, that something of big dimension is mapped by all these matrices to a smaller dimension. So that's the exact analogy. Okay, so the condition is analogous, and the question is, what is the progress measure that we are going to employ so that the changes will be quantifiable? There'll be the determinant of the scaling factor. These, keep changing by the determinant of the scaling factor, and we'll preserve the property of, being, we can convert it to a doubly stochastic or not. So I'm not going to define for you this, but let me tell you one thing about the three properties that are needed to prove. So here is what Gurvits does. This is easy. This is like in the first case. This is also easy. This is the same. Everything that's multiplicative under determinant has this property. By the same AMGM, somebody asked me in another talk whether you need to quantize AMGM. You don't. The same AMGM proves that it works here. So the only missing element is a lower bound on the initial value of this progress measure. Okay. In the case of quantum permanent, Gurvits simply proves it, and he simply proves it when we are in a compression space. He proves that it's exponentially small. And let me tell you more specifically what he proves, which we generalize. But, okay, I'll just one word before this. So he proves it for a compression space, and then he says, but if it's not a compression space, it's possible, he gives an example, where the quantum permanent is 0. So it can be 0, so it's no good. This progress measure is no good because it's a multiplicative increase and you start at 0. And then he says, why don't we try capacity? And capacity, the main problem, again, for a compression space, you can lower bound it just as we want here. But if it's not a compression space, you cannot lower bound it. And the way he lower bounds it, both in the case of a compression space, is the following. Proves the following theorem. So that, and it's very simple. It's just from the definition. If the determinant of L is non-zero, is not identically 0, so there exists mu I such that some mu I AI is non-singular, over F, or the base field here will be the complex number. So if there is some matrix spanned by our original matrices which is non-singular, then the capacity of L is at least exponentially small in minus, well, maybe I can write it down more specifically, 1 over Bn of n. I didn't define capacity yet, so I'll define it and then I'll tell you what we do. So capacity is a measure that you can use, and in a compression space, singular rank and non-singular rank, there's a commutative rank and non-commutative rank are the same. So since we're here in this algorithm, like in this algorithm, we are assuming that we are in the non-singular case, this will work. This will give we have a lower bound, which is an exponential on the initial value, and so we get a polynomial time upper bound. Okay, so what is this capacity? Capacity of an operator, L, or, well, L is just A1 up to AN, is the minimum over all PSD matrices for which determinant of P is 1, determinant. Okay? The minimum of all of them of the determinant of L of P. Why is this a capacity? Why is it a capacity? Well, he doesn't offer any intuition, and he says that quantum people may not like it as a name of. I mean, you can think of this. It's natural to think of a completely positive map as a channel. There is some. I mean, you can think of it as a channel. There is some. You do something to a quantum state. You send a sum to the quantum state. You get some other quantum state. So something happened to it. In fact, you can even give meaning to what it means, rank decreasing. So what is the case of rank decreasing? In some sense, you are killing some of the correlation or some of the entanglement in the state P. If it's a density matrix, you are killing some of its internal correlations. But I talk to some people who do.
Not the entanglement necessarily, because it's a density matrix.
It's a density matrix.
Like a distribution of the quantum states.
Yes, but it's still.
Reduce the total dimension of the entire space.
You reduce the for a subsystem you reduce the dimension. It's not necessarily. It can map the space to itself, but some subspace is right. That's right.
Not necessarily entanglement that it reduces.
So it's not necessarily. So I don't know. I don't have intuition about this. It's certainly you can ask about another interesting question to ask is about the von Neumann entropy of what happens to the von Neumann entropy of this quantum state. It turns out if you have a trace preserving map, then it doesn't reduce the von Neumann entropy. But that's not enough. So anyway, we care about some other condition. I talked to some people in quantum, and they don't know a natural.
So why determinant?
Okay, so let me.
Why do you bound the determinant?
Because, so I'll tell you where his intuition is coming from. So it's not, I don't know that it has a quantum interpretation. I just don't know. And he doesn't offer one, and he even says, he sort of mocks himself to some extent. But I'll tell you why he picked this. It's multiplicative under determinant. So if you change the operator L by, let's say, pre-multiplied by matrix B, then the whole value of capacity change multiplicatively. And similarly on the right. So that's one reason. So it satisfies the kind of property you want from the algorithm. And the other reason is that this is a quantum generalization of a measure that he, together with Yanais, defined in the classical case. So after our paper, I mean, I don't know, it's not it's never published. But the Gurvits and Olivera have a paper in which they have another analysis in this classical case where they give another multiplicative measure here. And this multiplicative measure is more or less a KL divergence. You have to define the distribution, but it's more or less a KL divergence. It's rather than telling you the KL divergence, let me tell you the analysis, the analog, let me call it capacity prime for a non-negative matrix. Now it's, you remember Aij are non-negative, so I'm back to the classical setting. It turns out that here you can define it as, just look at how analog it is. Minimum over all vectors which are non-zero, and their product xi is 1. So it's just the case that P is diagonal. Maybe I should call it P, vector P. Minimum of the product of AP I. Okay? The log of this gives you something that you should recognize as KL divergence. But doesn't matter that. This is multiplicative under these diagonal transformations that we do in the classical case. And the analog of this is exactly this. So at least he had a reason to define this without thinking about anything quantum. There is a reason to define this. Okay? Now, because of this definition, this theorem, which I wrote, this theorem is very simple from this definition. It's just simple. You have bounds on the entries, and it's some minimum of a determinant. You can simply get an exponential lower bound. But remember that in order to get this lower bound, we needed an assumption. We needed that there is a non-singular matrix in the space. So really the argument is there is a non-singular matrix in the space. We can get it with small coefficients, right? Like Schwarz-Zippel, we can get it with small coefficients. And then we are computing the determinants of numeric matrices, and you have to do something, but this is easy. So the only problem is we don't have this guarantee. So from this guarantee, you can see that he gets his algorithm for compression spaces. For us, this may not hold. It may be the non-commutative rank is full, and the commutative rank is not full. What do we do? Very simple. We do what we have to do. So we just blow the matrix up with big matrices. We know that even though the space is singular, we know that there exists. So for this D, which is at most exponential in n squared, there exist matrices Mi in MD of this let's see, such that sum of Mi tensor AI is non-singular in F in C. Right? I mean, that's the definition of D of n. We can blow it up so that we get a non-singular matrix. So now, the only thing remaining to do is to relate the capacity. So in this thing, we can lower bound the capacity. We can lower bound the capacity just for Gurvits theorem. We immediately get that if we define the quantum completely positive map, so we look at a completely positive map, which is defined by M1 tensor A1 AM. If you define it, so let me call it M tensor L, this completely positive map, you can easily bound the capacity M tensor L as exponential. Just I'm applying the very bound that Gurvits has, only with a new parameter. This is nd by nd as 1 over b dn to the order dn. Right? I just substituted dn for n over there. We are in a much bigger space, exponentially bigger. And clearly, this is not going to be enough for us because this exponential is like doubly exponentially small. So the last thing, so I will not prove it because I'm way out of time, but it's really a two-line proof, just from the definition, is the main theorem, which I would say is a simple fact that we prove in our paper, is that the capacity of L is at least the capacity of M tensor L, and this is for any D by, so this is just as long as this is D by D, for any D by D set of matrices you put here, to the 1 over D. So you gain a D in the exponent. You get the dimension of this N, of this M in the exponent here. This is the only thing. Again, this is a very simple lemma. We prove it, so let's just see why we are done. We have this capacity lower bound on the M times L, so we just have to take the dth root of this. This is good, so this gets us rid of this D in the exponent here. But you note that D appears in the base, so we better have an exponential bound on D. And that we have by Derksen theorem. So because we had an exponential bound on D, we get an exponential bound on the first capacity, and the rest is polynomial time convergence. Questions?
So you don't need, so now that there is a tighter bound of B,
It doesn't help us.
you don't need this stuff, or?
No, you need it.
'Cause
Well, okay.
this is exponential, this is D.
The question is, how do you, yeah. The question is,
Okay, right? The
well, you need at least a lower bound without this. Yeah, you need something. Yeah. And I can say something about the, the combinatorial algorithm does use the fact that the dimension blow up is polynomial only, and it works directly, not via capacity and not via Synchron's algorithm. It does not do that. It looks at this completely positive map, or this new symbolic matrix, which is blown up by an n-squared factor, and it works directly with it. How it works directly with it, I'm not going to describe it, but the best analogy is to say that there is a linear algebraic analog of the augmenting path algorithm for perfect matchings. It's called the second Wong sequences. And, but it's a very natural analog of the augmenting path sequence for computing maximum matchings in bipartite graph in the linear algebraic setting, and it works with it. And that, that's an essential ingredient. The other ingredient is some theory of blow-ups that was developed by these guys, Ivanius, Kiar, and Dirks, and Subramaniam, and together it gives this combinatorial algorithm to do the same.